David here. Welcome to the channel. Today's all about systems with information. This is chapter 10 of the book, The Science of Systems. If you want to learn more about the book, you can go to davidsugar.com/book. There you can download a free PDF of the book. Additionally, if you want the paperback version, you can go to amazon.com and purchase the paperback. There you can see all the images we're going to review today in person. So, what does it mean for a system to have information? Well, one of the foundational approaches to understand information is through a term called Shannon entropy, here represented with the letter H. So essentially, a system denoted S will have information when the Shannon entropy is greater than 0. Now, Shannon entropy can have different units. A very common unit is the unit of bits. Now, this relates to how surprising a given message is. Is it telling you something that you otherwise wouldn't know? For example, if there's just an equal choice and it's just A, then you know 100% of the time you're going to get A. So there's no surprising attribute provided by that message. So that would actually have 0 bits of data. However, if the message can be A or B, and the message is A or B, then it would provide 1 bit of data. Essentially, it's more surprising information. It was 50% chance to be A or B because they're equal choices, and providing that message provided 1 bit of data. Now, if there were 4 choices, A, B, C, D, this will essentially provide 2 bits of data. So it's all about providing a message that tells you something that is not 100% chance of occurring. There's a lower chance of occurring, and essentially this will provide information. Now, getting into more specifics about how Shannon entropy is calculated, first, what's really useful quantity is called the self-information, and this is represented with the term I. And this is essentially just the information of one event. So what this is the log of 1 divided by the probability of that event. Now, the units of bits have the base log 2, but you can use other bases which have other units. And you see here, when the probability is 100%, like it's 100% outcome is going to occur, there's no surprising information, that log of 1 would equal 0. However, if the probability is really low, then 1 divided by a small number would be a big number. And so there would be more information. Now, what Shannon entropy is essentially this information measure, but averaged out across many outcomes. So it's the sum of the probability of X and the log of the inverse of probability of X. This could be thought of as like a weighted average, the expected amount of information to quantify many different events. Now, I'll just make a note that this formula is very similar to what the formula we saw with entropy, that it's the sum of the probabilities and the log of the inverse probabilities, except that Boltzmann constant is not included. So thermodynamic entropy has Boltzmann's constant, while informational entropy does not. Now, it's also important to note that informational entropy is looking at something different than thermodynamic entropy, or it can look at something different. It almost always is looking at something different, which is essentially the message provided by a given system at any level. So this could be like a transistor on or off. You know, the ink on a paper, is it the letter A, the letter B, or the letter C? Any message provided by a given system. So it could be a macro level effect. Entropy, on the other hand, the thermodynamic entropy, is looking at essentially the information missing about the energetic microstates. So it has to do with the energetic states, while Shannon entropy can relate to any kind of states at a macro level, not just the energetic microstates. And I'll just make a note, these are not equal to each other. Sometimes they're almost perceived as opposites. And a way that could be thought about is Shannon entropy is the information provided by a message, while the thermodynamic entropy is essentially all the information missing about the energetic microstates for a given macro state. So they're looking at something similar, but just kind of in a different way. Now, a few notes is that the thermodynamic entropy in a way sets the limit of the maximum amount of Shannon entropy. A system could not have more Shannon entropy than all the information missing about its energetic microstates. So the message provided by a system could get more and more message, but a system can never have a message that conveys more information than all the information missing about its microstates. So the thermodynamic entropy in a way sets the limit. Shannon entropy is often looking at macro states, the messages in those, and how those relate. Now, it's helpful to show some examples of how this weighted average approach in Shannon information is calculated. So we'll give some examples here using A and B. Now, these letters, A and B, can be chosen from a set of 4 options, and these are all equal options. So the first option says there's 4 A's. Well, these are all equal choice. It doesn't matter which one you choose, it would always be an A. So that message wouldn't tell you anything. It would be 100% chance of being an A. So we see that there's 0 bits of data conveyed by that outcome. However, if there are 2 A's and 2 B's, that means there's a 50% chance of getting either. And we see here, when you sum up the probabilities, this essentially equals 1 bits of data. Now, let's do another case where there's 3 A's and 1 B. In this case, it would actually provide slightly less, 0.81 bits. This is because the 3 A's has basically a 75% probability. So there's less surprising information. Now there's a little more surprising information on the B because it's only 25% chance, but when you add them up, the average expected information would only require 0.81 bits, so a little bit less data. So this shows how basically entropy is taking this weighted average approach when you're looking at the information, the surprising amount of outcomes provided by a given message. Now, one of the fundamental papers in information theory was Claude Shannon in the mathematical theory of communication. And this was thinking about communication systems, and information is really integral when it comes to information systems. Or information is critical when it comes to communication systems. So, one example here is showing a data system which has a message source. This is then sent to a transmitter, encoded, sent over a channel, then received, decoded, and then sent to a destination. So an example of this could be like a radio tower. The message, like a song, for example, is encoded into the radio waves. It's sent as electromagnetic frequencies, and then like a radio in your car or in the house can pick up those frequencies, decode the message, and give it to the destination. Now, as the message is going over the channel, it's possible for noise to be introduced into the system, which would add more disorder. And essentially, this could be seen with the radio, for example. If there's a lot of barriers or behind a mountain, the radio might sound a little choppy. On the other hand, if there's not a lot of noise, it'll be a very, very clear signal. So using this mathematical terms of Shannon entropy, you can quantify how much information was from the source to the destination, how much was lost to noise. And there's a lot of theorems that can be proven about how strong a signal should be to overcome noise, the noise expected in the channel, the kind of the capacity of the channel. And so this was a really revolutionary turn in physics, because prior to this in Newtonian physics is really imagining the world in terms of these different particles, these terms of building blocks. Information was nowhere in there. Now, all of a sudden, through Shannon's mathematical theory of communication, there is a mathematical way you can add on. All these systems can also reflect messages that are interpreted. And those have different bits of data at a macro level. There's not only this entropy, at the energetic microstates, but there can also be messages, songs, books. All our history is written as these kind of informational codes. And so this provides a mathematical theory to understand communication and exposure to noise. Now, one of the key quantities contained in this theory is mutual information. And that's essentially how much information is shared from the source to the destination. The source here is written as X, so there's the entropy of X and then the entropy of Y, how much is received. The mutual information is how much is shared. If the mutual information was 100%, basically 100% of that message from the source went to the destination. So everything about the initial message source could be created from the destination. However, if the mutual information was 0, none of the information was transferred. Essentially, the destination would have no information about the source. It would tell you nothing about where the source was. And then there's the mutual information can also be in between. You may get most of the data, but not all of it. A lot of times you don't need all of it to reconstruct what is, the highest chance for it will likely be. And so there's some theorems about how much mutual information is required to effectively reconstruct messages and things like that. And this relates to that communication model we saw below with this channel. And what's really important here is that in a way, all information is mutual information because information needs to be decoded in order for it to make sense. Information doesn't make sense in a vacuum. So it's all about interpreting the message, how much expected probabilities were there before it was interpreted. That kind of determines how many bits of data it contains. So a lot of times bits of data is thought as an isolated thing. This flash drive has this many bits of data, but that flash drive only really has that data when it has a mutual information with a computer or something else that's reading off the data. So information's a lot about the interconnection between systems and how much is shared. Now, information plays a critical role in physics when it comes to quantum information. We did some intros on quantum theory before, but just to revisit, one of the key aspects of quantum theory is that there is this quantum probability distribution. And this can be thought of as information, right? There's a probability of occurring, which is really related to the notion of information. One of the key equations in quantum physics is the Schrödinger equation. This uses term H. Now, this is the Hamiltonian, not Shannon's entropy, so just want to distinguish those. But the Hamiltonian describes the energy. And psi, that Greek letter with 3 top lines and 1 bottom line, is the probability wave. And so this equation describes how the probability wave changes over time, how it evolves over time. And that essentially lets you know the probabilities of a given outcome. Now, what's interesting is that Schrödinger equation also contains the symbol I, which is an imaginary axis where I squared equals -1. So this can allow to calculate like electron spin or light polarization. So it's really useful to calculate some of these intrinsic symmetries. However, when you're calculating the real measurable outcome, what probability would you see it observe or affect, you square the wave function, and that takes out that imaginary axis. So there's only real numbers when it comes to real measurements. One of the most common distributions seen is like this Gaussian distribution, also called a normal distribution, showed here. And this would describe that there's a highest probability around the average, and as it goes further away from the average, it dissipates. So a lot of wave packets kind of have this Gaussian distribution and other kind of distributions as different energies come together. And what's critical here is that quantum information is all about studying how these packets of probability evolve. Another really interesting part when it comes to quantum information is that this really provides a new way to think about what is the world made of. So in a Newtonian perspective, the world is really thought about as made of these individual particles that are always there when you're not looking. They always exist there. Now you can bounce light about it, you might interpret where it is, but when you're not observing it, it's always there. However, in quantum physics, it really provides a different view of the world. Now, there's lots of interpretations of how quantum physics should work, and there's not necessarily a consensus of how it should work. But regardless of what interpretation you take, it's radically different than Newtonian physics. One of the most common interpretations is called the Copenhagen interpretation. And this is basically saying that when you're not observing the particle, when there's not an interaction which defines position and momentum within uncertainty levels, without that interaction, the particle could be anywhere. The electron could be in this part of the probability, could be in that part of the probability, and essentially it's existing everywhere in a way, a superposition of all possible probable states. And when it interacts with something like light, then that interaction collapses the quantum wave probabilities and it defines it within certain uncertainty bounds. And essentially what this means is that interaction relationship is essential for definition. Without this interaction, it could be anywhere. Now, there's a lot of different interpretations. The Copenhagen interpretation is essentially the particle is everywhere until the quantum wave collapses, and then there's an uncertainty level which defines position. There's also other interpretations like the hidden variables interpretation, which is that these particles are existing in one location when not observed. However, the forces, the probabilities that guide them are non-local, which essentially means that changing one aspect of the pattern can instantly change the others. Now, gravity, electromagnetic field, these are all local field theories. There's a local disturbance in the field would need to cause change to a particle influenced by gravity, for example. However, in quantum mechanics, there's something called entanglement. For example, if there's a spin up electron and a spin down electron produced by a given event, after the event produces, before you measure any one of those electrons, it could be up or it could be down. It's a superposition of those states. However, if you measure one of the electrons and let's say it's up, following conservation laws and symmetry, then by definition, the other one would have to be down. However, this seems to contradict Einstein's theory of relativity because now it seems that information was gained about this other electron faster than the speed of light. It was instant. Well, this turns out to be a really interesting topic of quantum entanglement. And the only way that this can be described is having these non-local interactions. So if one did have a hidden variable theory of quantum mechanics that these particles are locally defined, it would require a non-local interaction. So these interactions could happen. So there's a lot of mysterious things. However you slice and dice it, the world is far different from a local Newtonian perspective with particles interacting. And these informational interpretation of quantum mechanics, there's another type of information interpretation, which essentially saying is that the building blocks themselves are essentially informational packets. So instead of thinking of the world in terms of particles, it's thinking them in terms of probabilities. And the interactions of these probabilities is what is essential to define a given outcome and collapse the probability field within a certain range of uncertainties. There's other interpretations, we won't get into all this, but like the many worlds interpretation, I'll just state that, which essentially, instead of the quantum wave collapsing, it branches into different worlds essentially. And this can be one resolution to quantum interpretations and essentially the measurement problem, which is what's happening during measurement. It goes from a probability to a particle. How does that happen? Is there some mysterious thing going on here? But many worlds is saying, well, maybe they're just branching off and this whole measurement is just how one aspect of the Schrodinger's quantum probability fields relates, but there could be other branches. Those may necessarily not be able to communicate with another, but this is one resolution. So there's lots of interesting things when it comes to quantum mechanics and information. But what's really important here is that regardless of what interpretation you have and how you slice and dice it, information is always going to be a critical piece of quantum physics, and that this idea about information actually plays a role in physical theories of how nature works at the smallest scales. Now, there's another kind of entropy seen in quantum mechanics, and this is von Neumann's entropy. Von Neumann entropy is the total measurable information in a quantum system. Now, quantum information, this von Neumann entropy, is posed to be conserved so that the total measurable information is always the same. Now, this may seem kind of interesting. One interesting place about this is that, well, the Shannon entropy can change, right? Some computers can have more or less bits of data. And also thermodynamic entropy can change. It's expected to increase with an isolated system. So how is it possible that thermodynamic entropy increases, there's more and more disorder, more and more information missing about the microstates, but the quantum information, the quantum entropy is supposed to be conserved? And just a quick note on the formula, the von Neumann entropy is using the trace, which is another type of summation, and the probabilities is the quantum density matrix used in quantum physics. So these are the probabilities of these quantum waves. However, there's a key difference between thermodynamic entropy and von Neumann entropy. Von Neumann entropy is the total entropy, measurable entropy in the quantum system, so after the wave collapses, while thermodynamic is the information prior to measurement. And as we just talked earlier about before with entanglement, sometimes when you measure one particle, if they originated from a symmetrical process with conservation laws, if you measure that one particle goes up, spin up, and following conservation, the other one must be down, then you gain some information about the other particle. So when pieces of nature are entangled with one another, measuring part of it would actually give you information of the other. So this entanglement actually allows these two seemingly contradictory things of entropy to coexist. That quantum information can be completely conserved, but at the same time, thermodynamic entropy can increase. There can be much more macro level information changes, even though the micro physics, quantum physics level is conserved. Essentially, as different parts of the universe are entangled with one another, if you measured those quantum states, you would gain the information needed to measure the other ones, and the quantum information would be conserved. However, before measuring it, it looks like the amount of disorder has increased. So this is a really interesting connection here between those two types of entropy. So entropy and information also plays a role in space-time and black holes. So black holes are really interesting, and essentially a black hole is when gravity is so strong that light cannot escape. And that's called the event horizon, where gravity is so strong, it bends light in and light can never escape. Now, what's interesting is that a black hole's entropy is proportional to the surface area of the event horizon. So this kind of leads one to believe that all the information about the black hole can be encoded on its surface. And this is really similar to a holographic pattern. There's also something curious about black holes, which is that there's this black hole information paradox. We just talked about how quantum information is posed to be conserved. However, when information goes near a black hole, it enters and it can never leave. So it seems like it gets destroyed. Additionally, black holes have something called Hawking radiation, where particle-antiparticle pairs near the event horizon, some of them get trapped inside the black hole. And the effect of this is that black holes radiate heat. Big black holes radiate lower heat, smaller black holes radiate more heat. So what this means is that a black hole will essentially evaporate over time. So this leads one to think, well, maybe quantum information is destroyed. It enters, we never know what happens, and then and the black hole evaporates through Hawking radiation. Well, we'll see there is one solution that utilizes the holographic principle, it's a little complex, but want to give a snapshot of the holographic information structure because this is a really interesting type of information system. Essentially, a holographic information system, it can encode three-dimensional objects on a two-dimensional surface. So this is showing a 3D hologram of a dodecahedron. However, this can be encoded on a two-dimensional sheet. As a coherent laser is shined through the sheet, the three-dimensional object appears. There's some interesting encoding aspects about a holographic sheet. One is that if each part of the pattern, so if I chop up the holographic sheet, so I just have a quarter of it, well, if you shine the light a certain way, you can actually gain all the 3D information about the object. The resolution will be reduced, but it still contains all the information. So it's kind of like a fractal order where basically all the three-dimensional information is contained throughout the 2D sheet. But if you have less of the sheet, you have a lower resolution, but containing the whole thing. So that's an interesting aspect of it. But in terms of physics, this could be a potential solution to the black hole information where essentially, we saw the entropy of a black hole is proportional to the surface area. Well, perhaps the three-dimensional information is really encoded on the surface, similar to a holographic surface. So more specifically, in this version of string theories attempt to combine quantum physics with gravity. It's been proven that there are an equivalence called the holographic equivalence, which essentially means that something called ADS space, anti-de Sitter space, and this space can fit inside of kind of space-time coordinate system. It's another type of space-time coordinate system, but it's compatible with typical relativity space-time coordinate systems. And essentially, all the information in this ADS space could be equivalently represented as a boundary, so a sheet. So all the 3D information basically represented as 2D. Now, this is different dimensions. That was just an analogy, but helps understand it. And it basically that the anti-de Sitter space can be equivalent to CFT boundary, which is conformal field theory, which is basically a field theory on a boundary. So how this boundary, so the idea here is that a boundary can have all the information and that can be perfectly equivalent to a three-dimensional information. So this holographic equivalence can potentially resolve the black hole information paradox because as information enters a black hole, it can really be encoded on the surface. And as the black hole evaporates through Hawking radiation, that information on the surface was then evaporated off, essentially. So basically, the information was never destroyed. It was always conserved in some process, even though it seems kind of different than normal. So this is a really interesting aspect of physics. And it also sets something called the Bekenstein bound, which is essentially that within any given space, the total maximum information that can be contained is not proportional to the volume, as you may expect. It's proportional to the surface area enclosing it. So that's been proven following these theories. So this kind of leads one to think about space and time through a holographic lens. Holographic applications can also be used in other fields, by the way, not just physics. But this is a really interesting connection between information, space-time, and some of the frontiers of physics. So getting a little more down to earth, we're all really familiar with computer systems. And this is using information in very practical ways. And essentially how computer systems work, they have a series of transistors that represents on or off, and essentially this can represent different logical operations, and combining them can represent logic, can represent math. Now, biology also processes information. Some people may call living information systems computational. Some may say they're not computational, they're something else. Regardless of how you call that, it's fine. There is information being processed. That is known. is it exactly a computer? I mean, it's not using silicon and transistors, it's using other means, but it's still processing information. So here they're, included here as DNA is also included side by side to hard disk and flash drive. Now, using these bits of data, the units of Shannon entropy, you can understand like the read-write speed, how fast, how many bits per second can it read and write, how much data density can be stored, the bits per volume, the data efficiency, how many bits can be processed for a given amount of energy, and the storage lifetime. So what's really interesting is that so flash drives improved a lot on hard disks. There's better read-write speed, there's better data density, and there's more power efficiency. However, it should be noted that DNA in our biology actually has a huge amount of data density too, and the power efficiency is vastly better than flash drives. The gigabytes needed to process for the amount of energy is a lot lower. So we may actually be able to learn from living systems when it comes to be able to process data efficiently. Now, there's also an interesting connection between computers and quantum physics. Classical computers, the one that we're typically using all the time, uses silicon transistors. This uses classical bits, where essentially each bit can be, 0 or 1, on or off, and each bit, the function of defining each bit doesn't relate to the other bits. They can be connected through processes, but each bit is either on or off. They don't communicate with others instantaneously. However, quantum information systems, quantum computers, can utilize some of these quantum effects like entanglement and non-locality, and essentially each qubit, instead of a bit, there's a quantum bit, which is called a qubit, has some really interesting properties. One is that the other qubits in the system can affect a given qubit. So basically the function of each qubit is entangled with all the other ones. And this can produce some really interesting ways to process information. There can be some algorithms that are a lot easier to solve. And so quantum computers, there's some new quantum computers that have been developed. There's not a lot of qubits in their systems, but compared to traditional bit-based systems. But this could be a new frontier in computation, essentially utilizing qubits, other aspects of quantum physics, and using that to elevate what we can solve with computers. So just to give a summary of some of these computational informational systems, we were looking at a normal silicon-based computer. Also want to highlight DNA. So a computer, has the data units are these kind of bits, and the states per bit can be on or off. And the states of n bits goes along to the n. So if you have 2 bits, that would be able to define 4 states. If you have 3 bits, you'll define 8 states, and then so forth and so on. Now DNA, there's different chemicals like A, C, G, and T. Those are abbreviations of different chemicals, and those help define which amino acids are used to build which proteins. And so essentially, there's 4 different options for these different chemicals. And that would mean that the states for n units would scale 4 to the n. Now in the brain, the brain's in their kind of informational systems seen in biology. These kind of information processing units could be thought of the neuron. And interesting, there is a lot of different connections between these different neurons. So it can be estimated that up to 7,000 connections. So there could be lots of different states. Is it connected 1, 2, 3, all the way up to 7,000? So the states grow really high, basically 7,000 to the n for each number of neurons connected. Using this approximation of 7,000, there's a lot of other variables involved. It's highly precise and controlled about which neurons connect to others. There's also different groups in the brains. But this is to show of information systems that are more and more based on a network, more and more connections. And basically the number of states can grow very high. This can create a lot of different permutations and basically allow the human brain to store immense amount of data, not by having a lot of neurons necessarily, but by having a lot of connections between them. Because that connections allows way more permutations than just having a large number. There are a large number of neurons as well, but the connections are the critical factor which allow there to be so many unique states and define so many different informational possibilities. Now, a quantum computer here is shown as a possibility that the quantum probability wave can be fully entangled, basically connected with as many more. So if there is a million qubits all fully entangled, then they would all be entangled when it comes to defining if is each qubit, on or off, or a range of values within this. There's kind of a sphere which it can be defined within. So there's another approach to computation, which is deeply related to complexity theory. And complexity is all about how hard is it to predict a given outcome. Now, this approach to complexity, basically the Kolmogorov complexity, is asking what is the minimum set of symbols needed to transmit a message without losing the detail. So how easy is it to compress the symbol? Now, if you see these letters, it says XY, 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 and there's 20 letters. Well, you could translate that to another message which says P. P's use a symbol for print. Essentially, print XY 10 times. So you've given an instruction for how to get those 20 symbols. So instead of having 20 symbols, basically goes to 7 symbols. Now, the right-hand side shows a random assortment of 20 letters, and there isn't necessarily an easily identifiable way to compress those symbols. So the Kolmogorov complexity of that would be higher. Now, I would say that there isn't a determined finite algorithm to find the minimum set of symbols, so it's not always known if you have the minimum set of symbols. So that's an interesting caveat there. And this is actually done commonly with computers. If you put images and then you save them as a zip file, the zip file works to compress it. So by compressing it, it's able to have lower data, but still be able to transmit the whole message without losing detail. Also, this is seen in like JPEG, which is a JPEG image. Essentially, it uses a compression method. So if two images, they may have all the same number of pixels. They may be like 1,000 pixels by 1,000 pixels, but they may have two different values of JPEG, the different amount of data. So after compressing them, one is smaller than the other. So basically, after compressing it, that would have the one with more data after compressing it will have a larger Kolmogorov complexity. At least using JPEG compression. There may be some other compression that we haven't considered, but through that method, it would have a more set of symbols. So another aspect when it comes to computers and complexity theory is time complexity. How long does it take, or how many steps? So you can make the steps go faster, but what we're really looking at here with time complexity is how many steps is it going on? Now, a linear time complexity means that the time to solve scales at the same rate as the input. There could be a constant. So basically the t, the number of steps or the time, equals c to the n, c times n. C is a constant and n is basically the number of input. Now, a polynomial time is that the time steps scales faster at a given power. So the c is not added as a constant that's multiplied, but basically t equals n, the input size raised to this c constant. And even though it's a lot higher, like it grows faster, it's still efficient, that it doesn't grow exponentially. It grows on a power scale, which is a lot, but it can grow faster. So non-polynomial NP scales exponentially. So the non-polynomial time scales very fast. Essentially, the time steps t equals 2 to the n raised to the c power. So this creates an effect that can grow much faster than polynomial time. And essentially, these algorithms are not efficient to predict. They're not faster than brute force testing all possible solutions. So one of the key theories in terms of computational theory is called the NP equals P problem, or NP does not equal P problem. The question is, do they equal each other? And this is asking about a certain subset of problems to say, for all problems that have a quick testable solution, that basically a solution can be quickly checked in polynomial time or linear time, can they also be found? Can they also be identified, solved basically without the solution in polynomial time, or does it require non-polynomial time? So for example, Sudoku is a game where there's different letters on these grids and they add up. Once you have a winning Sudoku solution, it's quickly checkable. You can easily check it in polynomial time. However, to generate those solutions, it can't be generated in polynomial time. It takes non-polynomial time. You have to check all these solutions and go through. There's not a quick, efficient way. So it's easy to check, but it's not easy to create. So a lot of these problems that we see in our world are very complex, and they're like this. So right now, it's unclear if P equals NP. It's the hypothesis is that it's not true. It hasn't been found. So basically, most people expect that there are these problems that can be quickly checked but not quickly solved. And this is a really interesting aspect of complexity theory and connection with computers and information. So another aspect of this is the difference between computable algorithms versus non-computable algorithms, or uncomputable numbers. And computable numbers are essentially those that can be found efficiently. So even though pi and Euler's number, for example, are irrational numbers, they have an infinite number of digits, there's an efficient algorithm to solve the next digit. Through proceeding, adding this given series, you'll get more and more precise results. However, Chaitin's constant and the busy beaver function, which are looking at the halting problem, when a computer will halt or not, there's not an efficient way to solve this. You have to just brute force check. Sometimes computers will halt, and then you'll have more probabilities that you can enter in the function, but there's not an efficient way. It's not just by increasing time steps you'll for certain increase the preciseness easily. So uncomputable numbers are essentially those that do not converge through more and more time steps. There can be unknown haltings that could go on forever, or when they're finally solved could drastically change its function. So it's not like it converges to one number, but it can bounce about. So this is often called computational irreducibility, that even irrational numbers and some other things that seem maybe complex are computationally reducible, that they can be solved in an efficient way. However, other problems are not necessarily computationally reducible. There could be uncomputable numbers that you can put them in a computer, you can calculate it, right? But there's not an efficient way to know that it actually converges to a given outcome. One of the really popular things nowadays that's seen in AIs everywhere is something called artificial neural networks. And they use a really interesting way to use computers to transmit an input to an output. This shows a very simple case where essentially there's an input and there's different nodes. There could be different layers, like a first layer, second layer, and these different nodes represent different rules. It inputs the various data, it processes the rules, and then sends it to the next layer or to the output. Now, this neural network is trying to check for something very simple. It's just looking at two pixels that can be black or white, and is checking, does this fall into a checkered pattern or a solid pattern? And basically the first layer nodes are saying, is the top node black or white, or is the bottom node black or white? And then the second layer is combining two of those nodes on the first layer to understand, does it fall in a checkered category, which goes to the checkered output, or does it fall in the solid category, which goes to the solid output? Now, this is a very easy example. You can see how the neural network proceeds. But what's really interesting about neural networks in general, they can expand this out. So they can have a very complex set of input data, like maybe 100 pixels by 100 pixels. And then maybe the output could be to say, which letter does this fall? Is it A, B, C, D, or F? Now, when people write the letters, there could be a lot of different variations of A, B, or C, or D, or F. But using a neural network, it can process this information. So here's an example. One shows the input data of a picture. And so one question could be to ask to say, is this a flower or not a flower? Well, in the other case, when there's just a couple of pixels, it's really easy to self-program the rules and figure out which rules would exactly lead to which outcome. But when it comes to a flower like this, there can be tons of different flowers, right? It's really hard to pick a rule, one specific rule. The typical way that this is used, and this is used all the time in artificial intelligence, creating these large language models and other large neural networks, essentially you start with a whole bunch of nodes, which are these rules, but they're all set at random at first. So then what you do is you input data, and then you see the results, flower or not flower. However, there's an external body or external data like test data, which verifies the results. It says, well, actually your model was wrong in 90% of those cases, maybe it was right in 10% of those cases. And then what you can do is you can find to say, through something called back propagation, you basically take those outputs, you say, how can I change whatever nodes I had there to get me better results? So you can slightly change the nodes, and let's say now there's better results. Now it's 50% of the time it's a flower. Well, now you can run that program, check it and get more test data and say, well, if you change these nodes to be more and more, then it'll be more and more efficient. What's really interesting about this is that the programmer, doesn't need to know how all the nodes work or all the rules. It's not like they've diligently programmed each flower and what it could possibly be. They just set random nodes, random informational functions, and then later on, comparing with test data, altered the nodes in such a way to improve test data. And they kept on doing that until it's really, really, really high verification rate. So even if all these images of weird flowers, it almost knows how to identify it all. It's almost kind of a mystery how it works, because it's just using math to figure out how to change the nodes to get a more efficient outcome, not necessarily trying to predict which nodes should be changed or which pattern should be used for which nodes. And neural networks represent a universal function where basically any input can be changed to any output. You can go from like text to text, you can go from image to text, you can go from text to image, text to sound, sound to sound. So you can go really from any function to any other function. Now, I'll just make a note that it's a lot different than solving something when it comes to like a physics equation, because physics equations are usually analytical solutions. So it's using math to create a precise result, and it's usually very compact. While these neural networks often have a lot of variables, and it's not a quick analytical solution which you can understand the symmetries and the structures involved. It's basically a practical way to get a result that works a lot of the time, but doesn't necessarily know the patterns of what's going on underneath. So another information system is in our brain, and we're constantly perceiving and making memories of the world. So this is a really interesting and complex system that cognitive science is still learning a lot about. We don't know too much about all the intricate mechanisms of the brain. We do know some visual, image is processed some places, auditory is processed other places. We do know regions and kind of like MRI scans of brain activity, but knowing all the intricacies, it's not like we know brains that to the same degree we know computers. Computers, we know exactly which orientations of transistors produce which logical operations, how those add up to give the total logical effect. We don't have that same degree of knowledge in a brain. We don't know how all the neurons add up to process information precisely. We do know some general things. One of the most, crude example of how this system works is essentially there's an environment. We receive sensory signals like through the eye, the ears, touch, that's perceived in our cognitive system, the brain-body interface, and that creates our perception of the world, of what we perceive. Now, I want to make a note that a lot of times this perception of the world isn't exactly what the world is, but more is an image, which is an effective representation of the world. So one common example of this is through visual illusions. You see here that the image on the left shows two parallel lines and converging rays to a center point. Now, when the lines are oriented this way, it looks like the lines are bent, the two parallel lines. But if you actually put a ruler up to it, they're not bent. They're actually pretty straight. Another example is that a circle is drawn with little divots where lines could be. And basically, the brain superimposes lines to say, oh, these little empty spaces, a line could fit there. And now it looks like the lines appear when you look closely. So the brain can add information. It can slightly change information. And essentially, our brain hasn't necessarily evolved to see what is true necessarily, but to evolve to see what is evolutionarily suitable. So it may be highly suitable if a tiger is running at someone to see that and run away. But when it comes to these, lines, it may be evolutionarily suitable to see them bent. It may save information. It may save memory resources. Maybe that's how it usually would be perceived in a 3D environment. So that adds some information. So it's important to note that our perception is what's evolutionarily suitable, not exactly what's perfectly there. So the brain uses some really interesting ways to memorize these vast amount of data. Now, one interesting aspect is how do we remember where we are in a given space? Well, there's different cells that help with that in the brain. One are called place cells, which essentially fire when you're in a similar place. And these are studies often done with like mice. When they're essentially near a certain place and return to that place, the same cell will fire. However, that's not like a terribly efficient way to do that because you basically need one neuron for each place. And there's a lot of places that you would maybe want to memorize. So the brain has some place cells, but it also has these something called grid cells. And where grid cells are really cool is that basically every time you cross over regularly interval places, and it's about a hexagonal arrangement, the same grid cell fires. So basically imagine you're walking on this 2D plane. Around these hexagonal grids, one grid cell will fire. However, there can be other grid cells with different orientations. So maybe the other lattice of another grid cell is changed a little bit, skewed another way. Maybe the distances are different or the same. And essentially, what this allows is that one unique place can be easily identified. Like, for example, this image shows 4 different grid cells with different grids. However, when you superimpose them, there's just one unique location. So the key benefit here is that you need much less cells to identify all the unique locations. Instead of having one cell for each place, you can just have different grid cells, and then all the permutations, all the connections between them would allow to define all these individual spaces. So the brain is using a lot of interesting techniques to be able to memorize vast amount of data. And it's a lot to do with interconnections, with not just that there's segmented memories and certain neurons or certain neurons fire for just individual things. That does happen sometimes. We see place cells and some faces, there could be cells that are more dedicated for certain faces. But a lot of times it's about the interconnections between the neurons. This allows a huge amount of permutations and allows the brain to memorize and store a vast amount of data. Finally, wanted to end today on cognition and consciousness. So this is one of the outstanding, fundamental questions in science about what is cognition, what is consciousness, and there's not necessarily a perfect answer today. However, there are some things that are known. There's a lot more cognitive science, and there's a lot more knowledge about what cognition and consciousness is. Now, one aspect about science is that following the unity of science, that basically, biology should be fully consistent with chemistry, chemistry should be fully consistent with physics, even though chemistry and biology can have emergent effects, something that may not be efficiently predictable by the lower level model. It should never violate the lower level model. These should be emergent effects. They should emerge. They should not be fundamentally new. So following the unity of science, consciousness and cognition should not be a fundamental new substance of nature, of matter. So it shouldn't require invoking to say, oh, there's atoms around, and then all of a sudden there's a little mind, we need something else in nature. Essentially, cognition and consciousness should be thought about as a phase. Different atoms can come together. It can create a phase of water, solid, or other things. So it's not a fundamental new property. It's just a property of how those emergent effects come about. Similarly, when atoms are arranged in certain ways, it can create the emergent effects of computation. When transistors are arranged in a certain way, be able to process logical gates, that can emerge computation. Similarly, with different biological components, a neural network arranged in a certain way, this matter should be able to have the phase of consciousness. So consciousness shouldn't require a fundamental new substance, but just should require a particular organization. And essentially, one of the goals of science, a long-standing goal, is to identify what are the precise properties required to have the emergent effect of consciousness. So this graph here shows there's a domain and then physical systems, and then what emerges from that would be a subsystems of those physical systems could have the effect of conscious systems. Conscious and cognition should be an emergent effect within physical systems. Now, there's also another approach to consciousness through autopoiesis. We saw this last chapter about what are the distinguishing quantities and properties of a living system. And this is essentially that a living system is a self-making system. Autopoiesis, basically auto self, poiesis making. And in this theory, cognition is really directly associated with autopoiesis. This was one proposed way to understand cognition. There's lots of other proposed ways. And this is basically to say that cognition is deeply related to the informational processes of self-making. Essentially, what this would mean is that an artificial computer would not be considered to have a cognition or something. Only living systems would have a cognition. So it is associating cognition with life. Now, it's not saying that cognition only occurs with human organisms. It says it can occur with any organism, even DNA, even a cell. That the cell will be the smallest unit of life. So some form of cognition, at least in this theory, would be associated with life. Now, there's other approaches to understand consciousness and things. And one is this integrated information theory. And this essentially doesn't just associate cognition with life. It associates it with everything. And the term used here is something called integrated information. Essentially, integrated information is how much causally related data is between the system. So for example, like a photograph, if I cut a photograph into quarters, the pixels of one quarter shouldn't really affect the other parts of the image. Each pixel is just defined by itself. So there would be zero integrated information. However, a neural network, like an artificial neural network, well, if I cut it in half, some of those nodes may talk to one another. So the effect could be different. The causal effects of the system could be different. So that would have integrated information. So in this example with integrated information theory, anything with integrated information would have consciousness. So even this artificial neural network would have consciousness. Even the internet would have consciousness. However, something like our brain would have an immense amount of integrated information. We saw how many synaptic connections there were. So biological systems would have an immense amount of integrated information, which would mean they would have a lot of consciousness. But at the root, this integrated information theory associates consciousness with everything. It could be something, in computers and something else. So I think there's a lot more questions than answers, even in the 21st century when it comes to cognition and consciousness. But systems theory and information definitely play a role. And one aspect to think about it is, what information systems should be deemed as conscious, because I think it's clear that, maybe some shouldn't, like it's just some pixels on a paper just define an image, while others maybe should, ones that can relate to one another, ones that are integrated with one another, that form a cohesive whole that can causally interpret the world. But whatever it is, following the unity of science, it should be part of nature. You shouldn't need some other nature that this is physical nature, this is all about conscious nature. The whole notion of the unity of science is that everything should be unified and that nature as a whole is unified. So what we're trying to do is understand those patterns that allow consciousness to emerge. Thanks for tuning in today for information. Next up, we're going to switch to applications, and it's going to be all about sustainability. If you want to learn more about the book, go to davidsugar.com/book. There you can download a free PDF. Additionally, if you want the paperback, you can go to amazon.com. Thanks for tuning in. Have a nice day.